Yeah, sorry. Mm, yeah. So some algorithms are uh, mm, uh, uh, are kind of called greedy algorithms. Some algorithms are called divide and conquer algorithm. Some are called uh, basically recursive algorithm, or you can some special case of it is the dynamic programming algorithm. So you have not seen dynamic programming algorithm, but you have already seen divide and conquer algorithm and greedy algorithm to some sense in the class already. So, so we will continue looking at the graph algorithms, and then we possibly can go into a little bit of the string algorithms on strings or algorithms on numbers and so on. And this is how we will continue for another 4 weeks or so. And then we will be going into some special algorithms for which we don't have very good algorithms. I mean, sorry, problem for which we don't have very good algorithms, or very fast algorithms. And that will be more towards, I mean, a bit of a complexity theory kind of stuff like that, the NP completeness and all. So this is how we will be going in the next few classes. Okay. So if you have been following whatever has been going on in the first half of this course, and if you are reasonably comfortable with whatever happened in the mid-sem, okay, so you are more or less fine. So now, of course, the algorithms will become a bit more complicated. They will become a bit more trickier at times, but otherwise, I mean, in some sense, the conceptual part of most of the algorithms have been already been covered in the first half. Okay. So having said that, so let me kind of start sharing my screen. That might be useful. So sorry. Yeah. So we have been dealing with the concept of shortest path problem, right? Shortest path problem. And in the shortest path problem, we kind of have looked at basically the Dijkstra's algorithm. Now you should be comfortable with the Dijkstra's algorithm now. But one particular problem with the Dijkstra's algorithm is that although it's a very nice and beautiful algorithm, but it cannot handle negative weights, edge weights. So the next question is that how can I design an algorithm that can handle negative edge weights? Okay. Now, this is where I think, of course, we have already discussed this one earlier, that if a graph has a negative cycle or a cycle whose weight is negative, then shortest path possibly doesn't make much sense. But then there are graphs where there is negative edge weights, but not negative cycles. So we can assume, so we can still assume that no negative cycles. Okay, so basically I've been given a graph in which there is no negative cycles, but there are negative edge weights. Now, how do you compute it? How do you find it? Okay, fine. Now, so in the case of the Dijkstra's algorithm, what was done was kind of a greedy algorithm, right? That okay, what is the I mean, for every vertex, we are trying to find out which vertex can we reach first in some sense. Okay, so this for the particular vertex, I have already managed to find the shortest path from S to that vertex. Now I want to keep on adding one by one, kind of stuff like that. Okay. So here, one thing that one can do is, okay, first of all, we have to ask the correct question. What is the shortest path? Right? So one way of formalizing it is that, okay, see, there are lots of cycles that are there in a graph. A directed graph might have cycles. So we want to kind of take care of the cycles differently. Okay. The fact that we have no negative cycles, what does it mean? That means going around one cycle multiple times, or going on at even a cycle once also, is completely useless. Right? So if you have a path from S to T, and that kind of goes like this and makes a cycle here, and then goes up here and then back here, this cycle over here is useless. So this cycle has positive weight, right? So this, you have basically spent from here to here, you have spent one extra cycle, right? This one thing has a one extra cycle round. So your cost has been only been added, because we are assuming that there is no negative cycles. So we can assume that no such cycles exist, right? So the shortest path from S to T must be a simple path. Simple path meaning a path without any cycle. It's a path. It's not a walk.
Sir,
Yeah.
this cycle meanings are negative cycles or any cycles you are talking about?
Any cycles.
For
There
the
is no negative cycle. Start with assuming that there is no negative cycle. Okay.
So for the concept of the shortest path, we are just assuming that there will be no cycle.
There is no negative cycle. No, yeah. For concept of the shortest path.
Okay, yeah.
The shortest path from S to T will not have any cycles. Okay. I mean, I think it is not useful to have any cycles. Is it clear?
Sure. Okay.
Okay. I mean, if you have a cycle, then you are only making the cost of the path go higher up. Okay. So that is not useful. So we can assume that, so we can always assume that the shortest path from S to T is a kind of a path. So one thing that we know, therefore, is that therefore the shortest path from S to T has at most n-1 edges. Sorry, no, I'm making mistake. Not n-1. Actually, yeah, n-1 edges. Okay, right. So at most n-1 number of edges, or v-1 if you want to call this one v.
Sir, what is n?
Yeah, size of some number of vertices. Okay, number of vertices, number of edges. Okay, so now, okay, good. Any questions so far? So this is something from now on. So since till now on, many of the algorithms that we have seen, or the Dijkstra's algorithm, although it might look very nice and all, but it is what you can call it as a greedy algorithm. Okay, it's meaning you are actually progressing in a greedy way. Okay? It is something similar to the bubble sort. Okay, where you do something with a guarantee that you are not taking a wrong step, but you are not trying to kind of optimize your time complexity that much. I mean, you are doing things which is the right thing to do at that stage, and that's it. But if you have any idea from sorting algorithms, it is that this bubble sort kind of algorithm, or bubble sort of selection sort kind of algorithm, are not necessarily the best, right? The better algorithms are where you either use some kind of a much more complicated data structure kind of stuff like heaps and all, or you use some kind of a recursion, some kind of a break it up into small parts, okay, like a merge sort. And that is one way of making progress, making a quick algorithm always. Okay. Fine. Okay. Now, okay. So can somebody say how can we break this one into smaller parts? So I want to find out the shortest path from S to T in at most V minus 1 number of edges. How can we solve it? Can somebody solve it into a recursive way? See, here is the graph that I have. Here is the graph. Here is S. Here is T. I want to go from S to T and I want to find out the shortest path. I want to find the shortest path from S to T using V minus 1 or at most V minus 1x. Okay. I want to solve this. How do I solve this? Any idea, any suggestions of how we can kind of break it up into smaller sub problems kind of stuff? Nobody has any clue?
Can use DFS starting from S.
I can use DFS starting from S, but that will only tell me the ages, right? So they will not have the weights. See, I'm not saying that I'm trying to look at the shortest path starting from S. Okay, by the way, when I'm saying shortest path, this is not that number of ages is minimum. This is the sum of the weighted ages, sum of the weights of the ages in the path.
Okay, then Dijkstra.
Sorry,
Dijkstra algorithm.
I cannot understand. Dijkstra's
Dijkstra
algorithm?
from S.
From Dijkstra's algorithm?
You have to start from S and start Dijkstra algorithm.
You mean Dijkstra's algorithm, right?
Yes.
Yes, but what happens if the sum of the ages are negative?
Hello.
Some of the ages might be negative.
Hello.
Yeah.
So you can look at the neighborhood of the vertex T and you remove the okay, you find the point where it has minimum edge weight, then from S to that point W to find
Okay. And
then add this edge to edge between W.
okay, good, very good. I see what you mean. Okay, very good. So see, this is one way. This is something that we had kind of discussed it in the earlier class also, if you remember. Okay. So look at all the vertices which are the neighbors of T, pre-neighbors of T. Okay. So say they are say U, V, and W. Okay. So what I want, what is the problem that I want? I want to find the shortest path from S to T in G, right? G is the weighted graph. So I said that what I do is that, okay, what is this? This is that, look at all the vertices from where you can go to T, right? So for all those vertices, okay, so let's consider the shortest path from S to V. Okay, now if there is a path that is takes less than or equal to n v minus 1 edges, then the path from S to V takes at most v minus 2 edges, right? So look, let's look at, take a u which is in the neighborhood, so negative root of T, meaning they are the in neighborhood of T, from where there is a edge to T. Okay, and for that u, what do I want to say? I'll, okay, go and compute the shortest path from S to U in G minus T. Okay, now this will be the shortest path. Oh, I'm not told you a very good important thing. And I have this v minus 1 over here, right? Say I have this v minus 2 over here, I can write. And I'm just interested in all the paths of length v minus 2 from here, from U2, right? And in that case, what is the shortest path from S to T via this path? This would be this plus the weight of U comma T, right? So the plus the weight of U comma T. This is the amount of cost of this edge. This is the best path from S to U using v minus 2 edges, right? So in that case, I will be able to go from here to here in less than or equal to v minus 1 edges, and take the minimum over all such U, then we get that answer.
Sir, one clarification.
Yeah.
So actually, we are considering at most v minus 1 inches because we are don't consider any loop under shortest path, right?
Yes.
Okay.
Yeah. Okay. So this is a very, I mean, this is something that we have done in the earlier class. So this one would give you the best shortest path between S to T in v minus 1 edges. V minus 1 using v minus 1 edges, right?
This is like brute force only.
This is just brute force, right? This is almost brute force. I mean, although I'm assuming using this, I am what is it called? Yeah, I'm using this kind of a sub thing, okay, but it is kind of brute force. Now, what is the time complexity of this one? Let me ask you guys. What is the time complexity of this algorithm?
The order of n square, right?
Order of?
N square. That is the number of.
Why is it order of n square?
So actually, it's considering first the v minus 1, after that v minus 2, and dot 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 up to 1. So
But
the
then there is a minimum over all of them. So you have to compute this one for all of them, right?
oh, okay. Yeah,
So the way in which any recursive algorithm can be done is that this algorithm says, so so this one takes time t of n because g is of size n, right? This is also n. doesn't matter. So this is, I have to compute this one. So that is T of n minus 1. And then I have to do it for all possible. So this is basically the degree or mean degree of T, which in the worst case can be n into Tn minus 1. So this is basically n factorial. So are you following this?
Yes, sir.
By the way, if you are not following this now, okay, I will increase my pace a little bit in this second half of the course. If you are not following, please stop me. I will repeat it. Okay. But I will be possibly be going a bit more faster than earlier. But so see, remember this one always. This is something that you should remember throughout your life. That if you have a recursive algorithm where a algorithm calls itself on a smaller input, then the only way to compute the time complexity is using a recursion. The only way. Okay. So here T of n denotes the time complexity taken when the graph size is n. Now graph size goes down to n in this step, right? N minus 1. So this takes T of n minus 1 time. This takes T of n. So, and I have to do it for all the in neighbors of T. So I get T of n equals to in neighbor of T, in degree of T times T of n minus 1. Now in degree of T can be, in fact, it can be n minus 1 or something like that maybe. So this becomes maybe n minus 1 factorial, but whatever. This is order of n factorial. Is this fine? Okay, this is not what they wrote is wrong. This is not order of n factorial, but yeah. So let's leave it with this one. This is exponential. That's all that we have. Is it clear? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. But do you think we can do better? Think of this example. Okay. Maybe I will draw a couple of edges here in this graph. I have an edge from here to here. I have an edge from here to here. So you see the edges, there are two more edges. In the first step, there is nothing that we can change, right? Right, first step is fine. So when you are trying to solve this, you are calling this S U G minus T V minus U. Right? Fine. But now you are saying here, so you want to solve this one, ST STV. Yeah, go ahead.
Actually, like look at this just this subgraph and try to do shortest path.
I cannot. Can you speak a bit louder and
Sorry,
sorry?
sorry, it's not a. It's not clear.
Okay, okay. See, so basically, if I think of it here, I will use a different color here. So you will be running. No, this is not a. I don't mean this is an arrow. Okay, I didn't mean this one. But I'm saying that you will be running this SP SV from here, right? You will also be running SPSW here. Okay, that means what about this remaining stuff? So you want to compute the shortest path of length k minus 1 from S to V. You want to compute the shortest path from S to V in S to W in K minus 1, right? Now, when you are calling this one, what is the next step? Think of it. At that time, this one is out, okay? This one is gone. We are talking about in GT minus 1. So I want to possibly go to its previous one after that, right? SP, my shortest path from S to V, to calculate that, I want, because there is an H from U to V, I want to go to U and then, okay, what is the shortest path from S to U in V minus 3 steps, right? So this is the first round, right? In the next iteration, or maybe this is how you can write it one, okay? So I am writing it as SP, say SU, say N minus 1, right? So, sorry, it's not correct. SP. Then I am calling from here 3 things: SP, SU, N minus 2, SP, SV, N minus 2, and SP, SW, N minus 2, right? So I want to compute the shortest path from here to here, and I am going through all the possible 3 in neighbors of T. I'm going to call it, right? Right. So this is how, and how I'll do it, I'll take the minimum over all of them. So minimum over all of them will give you me this result. Any questions so far? No, I assume. So now let's see here. What will be the next step here? See, maybe that V has some edges, some other edges, okay? I don't know. Maybe W also has some other edges. But am one of the edges from U to V, right? So U is in the graph of V, right? U is in the in neighbor of V. So in that case, I will have SP, S, U, N minus 2 here, N minus 3 over here. Maybe I have some more other edges, right? Similarly, since U was in the in neighbor of W, I will have SP, S, U, N minus 3 over here, maybe some other stuff, right? So if since we wrote the recursive thing like this, right? When we are unfolding it into the tree structure, that for this one, I am to call this so many times, right? And for each of them, I'm unfolding it, right? So what you can see is that it might happen that the same thing is being called twice. Do you see this? Hello.
Yes, sir.
Good. So you see this issue, right? So what is happening is that a sub problem that would come in the recursive tree of the original algorithm is being solved multiple times possibly. Okay. And that is something that is way too costly. Why should it be done multiple times? I just need that answer. Why can't this answer be used here? I can, except that my algorithm has been written in such a way that it has been computed a multiple times. So think of it in this following way. Okay. So you have 10 tasks. Okay. So what you told is that you have given this 10 tasks to your 10 friends. Now each of those friends have broken up their own task into 3 different subparts, and they've given each of those subparts to their friends, and so on and so forth. But while doing this breakup, some small subpart, your first friend's second friend is also doing, and your second friend's fourth friend is also doing. So the same subtask is being done twice, maybe even more than that. And that is just wastage of computation. Okay. So that is also the why this is becoming so costly. That we are computing the same thing again and again and again and again. So the question is that how do you save this? How can we work around so that we don't have to repeat the same task again and again? Any suggestion?
So we can use some distance matrix kind of.
Can you some distance matrix
Yeah.
for what?
Saving these distances like from S to U, S to.
Right. I mean, maybe you are saying the right thing, except that, I mean, this is not what I was expecting, but okay, let me ask a few more of the other of your friends. Mayank, Deora, do you have any idea how can we help it?
Yes, sir.
Sorry?
Sir, hello.
Yeah.
Yes, sir. Sir, we can start from one age.
No, I don't want us. You are giving me a solution, right?
Sir, sir, actually, I know this.
No, but tell me, what is supposed to be done?
Sir, first we find for one age containing one age.
That's what I'm not asking you to repeat the algorithm.
Oh, yes, yes.
That's why I'm not asking you to repeat the algorithm. Tell me, how is it that we are going to save these recomputations?
Marking whichever is done as some other color.
Okay, that's one thing, but more than marking, just storing them. Right? If you can store them, if I store them once, then when the next person needs to do that, that person can take a look at it and be done with it. Okay, that is the simple thing. If a computation is done repeatedly, one after another, I mean repeatedly in a single computation, then the basic idea is store them. Once you do the computation, store them in a nice way so that when the next time it has to be done, it can be reused. This is the most simple thing. I know that many of you know the algorithm that I'm going to talk about, and you can almost say it almost by heart what the algorithm is. But that is not the goal that I want to do. Okay. My main goal is that why is such an algorithm useful, and what is the difference between that from a normal algorithm? And it is just this very simple concept that if a computation has to be done multiple times, okay, store them. And this so-called very simple idea is what is known as dynamic program. Something that usually is considered to be one of the trickier things to master. Okay. And that is it. We will store them and do it. And let's see after that what happens. And if you unfold the algorithm, what we will get is something nice. So let me now switch to the slides and try to explain you the actual algorithm that I wanted to explain. Yeah. So, do you see my screen again?
Yes, sir.
Yes, sir.
Yeah. So we are doing this. So this is what is called the Belmont-Ford algorithm. Again, I know that many of you know the algorithm and can repeat it by heart. But again, that is just the where I think the teaching of ISI and many of these things differ. The goal is not to memorize an algorithm. Okay, the goal is to understand why that algorithm has been done in that particular way and what is it achieving by doing so. What are the negatives of that and what are the positives of that? Okay, good. So, okay, so to quickly go over it, just to make everybody in the same page. So there are edges which have been assigned some real numbers, and we are talking about the path length is basically sum of the weights of the edges in the path, and we are interested in the shortest distance between u and v. Okay. The weights can be negative, and we will be assuming that there is no negative cycles. Okay, so this is the kind of state. So we have no negative cycles, but edges can be negative. So the problem is that, okay, so sorry, I made a mistake here. So this is not positive, should not be there. It should be the given a graph with edge weights. Find the shortest path between u and v. So this positive should not be there. And we have already seen an algorithm in this direction, right? The Dijkstra's algorithm. I don't want to go over the Dijkstra's algorithm all over again, but I mean, this is just going over this algorithm. But the most crucial part of this Dijkstra's algorithm is that, okay, it's a very simple algorithm. It's a kind of a greedy kind of algorithm, and it has the running time of order v square. Because every time for every vertex, so you have a loop that runs the v number of times, and every round takes v number of steps. Okay. And I have not gone over this whole thing, but there is a very nice way of storing some information so that you can even reduce the run time from v square to something like order e plus v log v. This is a pretty nice algorithm, no doubt. But crucially, this algorithm's correctness depends on the fact that all the weights are positive. If the weights are not positive, then this algorithm does not give you the correct answer. And a quick way to see this thing is that, so all I have done is that I have used the same graph from last thing, but this input, this age over here, it was +8. I have just made it to be -8, the age weight. And what you can see is that the algorithm will go exactly as before, but you can already see in this state only, already it has been declared that, okay, E is of size, or maybe even the last step, okay, that E, shortest path from G to E is 9. That's the first step that you have done. But actually, it is not 9, it is 3. You go to F and go to -8. It is 3. And you see that even in the first step of the Dijkstra's algorithm, the Dijkstra's algorithm makes a wrong mistake. And basically, it just never is in a position to rectify it. Okay, so this is the problem of Dijkstra's algorithm. Dijkstra's algorithm cannot handle negative edges. Okay. Now, how do we handle negative edges? And the main idea is what I just explained to you guys in a high level is using dynamic programming. Now again, I told you that we are storing things and storing information and so on, right? So this is the main idea of dynamic programming. We will be seeing 2 or 3 other dynamic programming in the next few weeks, but the basic idea always remains same. Okay, take the bigger problem, break it down into smaller problems, sub-problems, smaller simple sub-problems. Now, not only solves those sub-problems, but also stores the answers in a table, so that when that sub-problem is required in another tree of the another path of the computation tree, it can be reused. Okay, and of course, this last statement basically is a typical recursion kind of stuff. You come up with it's a recursive algorithm of problem. Basically, you take the smaller problem to define a bigger problem. So basically, again, I repeat here, if you want to design a dynamic programming, you start with a recursive algorithm and then try to come up with some this clever trick that helps you to gain a lot of computation power. Okay. So what does it come down to? The shortest path thing. So basically this is what I will be storing. Okay, I will be storing this concept DLV. What is the DLV? So I start with this. So I am interested in the shortest path from S to any other vertex. So DLV is the length of the shortest path from S to V using at most L edges. This is exactly what we just defined, that SP, SU, n-1 or n-3 or whatever, right? So note that here, so DLV or D n-1 V, where n is the number of vertices, gives you the correct answer, right? And the main idea again is exactly what we told, that if you have DLV for all the other vertices, then I would be able to get an answer of DL plus 1V from those. Okay. So to start with, of course, what is D1V? It is the shortest path from S to V using one edge. So the only thing that can happen is that there has to be an edge directly connecting S to V, right? So we define it as this one. Okay, D1V is the weight of that edge, because see, at this point there is no other edge, right? That doesn't mean that this is the final answer, by the way. D1V is not the final answer. D1V, the final answer of V will be Dn-1V. But to start with, D1V is the weight of the path from S to V, which uses at most one edge. Okay. And at most one edge meaning you can only use the edge that connects them, right? Nothing else. So this is kind of, you can think of as the base case of this recurrence. Okay. Now, of course, for any other vertex that is not in the neighbor, D1V is infinity, because there is no path of length 1 which uses the at most one edge to go from S to V if V is not in the neighborhood of S. So this 2 actually, this 2 is the base case. And how do I design the recursive algorithm? It is this. Okay. Again, always think of it as your friends kind of stuff. Okay. So DLV. So all your friends have come up and they have all told that, see, okay, that I know the shortest path from S to V using L steps. So this person says, oh, I know the shortest path from S to U using L steps, and so on and so forth. Okay. So what you want to calculate the shortest path between S to V using L plus 1 step. So what is it that can be done? Okay. So it must be therefore that either the shortest path from S to V using at most L plus 1 step or L plus 1 edges uses actually less than L edges. So in that case, I will take this one. So this is the shortest path from S to V using L edges. But if the shortest path from S to V uses exactly L plus 1 edges, that means there is a path that goes from S to V via some vertex. It enters V via some vertex, and that must be U, which is such that U and V, there is the edge from U to V. So in that case, you say, okay, you ask your friends standing at U, what is the shortest path from S to U using L edges? Your friend says you an answer. Okay, so from S to U using L edges, I can reach using with this cost. Okay. Now, if I have to go one more step, this is the cost that I will be charged, and so total charge will be this, and therefore this will be equal to, I can say, is the minimum of these two objects and among all possible use. So is this clear, this idea? Hello? Hello?
Yes, sir. Understood.
Yes,
Yeah,
sir.
yeah.
Okay. If you have understood this one, then good. So, so say here is basically the stuff that we do. By the way, you realize that this one, LU, DLU, and all those kind of stuff, DLV, these are the information that I'm going to store, and the storage is important. Okay, so let's look at this one. Okay, I want to look at all the vertices from G, all the shortest part from G. So to start with, what happens? Okay, so let's start with the 0 case, and 0 case, of course, I start with everybody infinity and G is 0. The next step is, as we told, that let's look at all the neighbors of G, that is basically E and F. And I will say, okay, to go to E using one step. So this step is basically using one step, right? Using one step, I can go from G to E at cost 9. I can go from G to F using step 11, and the rest of them are all infinite. Now for the next step, how many of can I reach for 2 steps? Also, this is where this beauty comes in, right? In the 2 steps, I am looking at, okay, what about E? Say, let's look at E. So I can either go from G to E using the previous one, which is 9, or I can go from G to E using, let's look at all the in degrees of E, which is F is there. Okay, F, which is means in that case, it will be -8 plus the previous F. So -8 plus this 11 over here, which is 3. Similarly, say for D, we have all of them, and so on. Okay. The next one is, again, I go for, say, for example, here. Okay, this is the number of 4th step. Okay. Okay, maybe they come back here. Okay, let's look at C here. What is the shortest path that I can go from G to C? So still, okay, for G to C, either I could have gone directly in one step, so which is infinity, or I could have gone through E. In that case, it will be 1 plus the previous E, so 1 plus 9 is 10. So okay, 10 is less than infinity, so this is 10. Okay, so this says that the shortest path from G to E, C by 2 steps is 10. Okay. Now the next step is 3 step. In this 3 step, what happens? How can I go from G to C? Okay, I can go from G to C either by the whatever we have gone earlier, which is 10 steps. Okay, or I can go for with 3 steps. That means I could have gone with to E with 2 steps. So how much is the cost of going to E with 2 steps? Now see, this has already been calculated. I don't want to calculate it again. G with 2 steps is written here. It is 3, previous one. So 3 plus 1 is 4. Oh wow, wonderful. So this becomes 4. So 4 and 10, minimum is 4, and that's why 10. That's why it's 4. So because note that this, if you unfold our original recurrence, you will see that this information, the shortest path from G to E, is being used many times in this whole computation. Okay, and you can keep on going like this, and basically you will be able to solve the whole thing, and at the end you will have the final result. So what is the correctness of the algorithm? So the main idea that is there is that you have DLV is the length of the shortest path of less than or equal to E L edges from S to V. So if I can prove this fact, this is basically what we want to prove. If we can prove this fact, then we know that Dn-1 V will have the right answer. So how do you prove this fact? This fact will of course depend upon how the DLV was defined in first place. DLV was defined in a recursive, right? So we prove it this way. Okay, so say if not, so if this is not the case, that means there exists. So here we are, by induction hypothesis, we can always assume that we know the correct answer for all L-1 things, for anything that is less than L, right? So for all K less than L, DKV actually outputs the length of the shortest path with less than or equal to K per edges from U to from S to U, S to V. So if not, then that means that there exists another path of length less than L from S to V. So consider the smallest such L. Okay, and let that path enters V through U. In that case, DL-1 V must have been the shorter path there, right? DL-1 V must be containing this path. So if not, okay, then the DL-1 V has already got a mistake, which by induction hypothesis is not possible. Or this is the shortest path, but if this is the shortest path, then I would have chosen DL-1 V plus the weight of V minus DL minus, this should have been U. This should be U, okay? This should be U. So DLU must contain the wrong information. Because if DL minus 1 U contains the correct information, then DL minus U plus weight of U to V would have given me the shortest path, and that would have been. Okay, maybe I rushed over this correctness algorithm to some level, but again, please go over this algorithm. It is not hard, but the crucial part that I want you guys to always remember, that one very powerful way of solving algorithm, when you have to design a new algorithm, it is by using recurrence. So design a recurrence first. And once you design the recurrence, then if you think that the recurrence is actually using the same thing multiple times, solving the main thing multiple times, then a simple trick is to store that information once, every time you solve it. And then you have a very good algorithm. So let's, for example, see what happens to the time complexity of this algorithm. Okay, so basically this is the kind of the Bellman-Ford algorithm. Basically, I go from 1 to n and I keep on updating this one. The div is equals to the minimum over all the u where you solve this one. Okay, note that although it is written in the recursive way, but the idea is that this information is not, we have to not recompute it every time. It is stored. Okay, so we have this table where you store it. Okay, if you want to solve this one, if you want to cite this time complexity of this algorithm in this by writing a recurrence here, it will be n factorial again. But to note the time complexity, look at here. How big is this table? How big is the table? Can somebody tell me how big is the table?
N minus 1 to n
N minus 1 to?
into n.
It is n minus 1 to n. So there are n vertices. And I will go down to n minus 1 steps, right? I mean 1, 2, 3, 4 to n minus 1. Okay, right now here it is 0 to n minus 1. So it will be n. So it is order n square size matrix that I'm solving. Now for, if I want to solve any one particular point, how much time do I need? To fill up one point? Think of the time, like say maybe we go back. Right now I want to fill up this slot, or I want to fill up this slot. How much time do you think do I need to solve this? I want to look at, right? So this is the, all this, I want to compute the shortest path between S to E, right? In whatever 1, 2, 3, 4, 5 steps, right? So look at this deduction here, right? This is what we have to do. You are doing it by taking a minimum over all possible u's. How many u's are there at most? N steps, n u's. So basically, every one of the cell can be computed by looking at one point earlier and or one point in the previous one plus the weight of UV kind of stuff, right? So every point can be solved or can be filled in order n steps. So the time complexity for this one is nothing but n square times n, which is n cube. So although it's a recursive algorithm, it is not being done in a recursive way because we are storing that data. And therefore, the update time takes order v steps, and the total number of entries in the table is order v square, and therefore the total runtime is v cube. And this is basically the algorithm, the total algorithm, the complete algorithm. Okay, so any questions? Was this fine?
Sir, this algorithm is fine, but can I ask a question?
Yeah.
So there are many algorithms which is recursive in nature, and in that algorithm we also store the result of sub problems to solve the main problem, but that is not optimization kind of algorithm. So can we say those problems belongs to dynamic programming category?
If you are, say again, yeah, basically that is, I mean, if you are, again, any recursive algorithm, okay, See, recursive algorithm doesn't necessarily mean that you are solving the same thing again and again. Okay. For example, merge sort is a recursive algorithm, and there you don't solve any subpart multiple times. You solve every subpart at most once. Okay, so recursive algorithm itself doesn't mean that some subpart has been solved multiple times. But if there is a recursive algorithm where a subpart has been or is solved multiple times, then storing that data or solving that subpart once and for all, storing that data is actually a very useful thing. That is the main idea of recursive algorithm. So there is nothing like which is a recursive dynamic algorithm, which is not a dynamic algorithm, and all doesn't matter. Nobody is interested in the classification of algorithms, but people are interested in the techniques. And the dynamic algorithm technique is basically if you have a recursive algorithm where the same in subpart is being solved multiple times, then store it. Okay, and the computation and in that case, when you solve the time complexity, then you don't do the time complexity using the recursive technique, because it is not a recursive algorithm after that. Because like here, for example, I mean, although we have written it in this way and it looks like a recursive algorithm, it is not a recursive algorithm because we are storing this data. So the calculation is not done through recursion. Time complexity. Time complexity is done in a different, namely, how much time does it take to fill up the whole storage set or the table and so on. Okay, so which algorithm is dynamic programming, which is not something of any use. But the technique is what is important. Yeah.
Sir,
Yeah.
if the graph has negative cycle, and if I
Oh, if a graph has
more than
negative cycle,
and if I loop it over more than n times, like I'm just
I am unable to hear you properly. Actually, I must
if the
say.
graph has negative cycle,
Yeah.
and if I run it over like more than n times,
Yeah.
this algorithm
Yes. If the graph has negative cycles, think about it. What will happen? Okay, you don't even have to loop it in more than n times or something. If a graph has negative cycle, it might actually very well end up producing a complete garbage. Okay. So one thing that you can think about is that use this particular algorithm to find out whether the graph has a negative cycle or not. Actually, this algorithm with a little bit twist can be made that whether this graph actually has a negative cycle. But if the graph has a negative cycle, then a lot of weird things will happen. Because the shortest, actually you will still be outputting the correct answer in the sense that you will still be outputting the shortest path from S to V in T steps. That is not a problem. But the shortest path between S to V will not necessarily be, so like here, here you end up at I equals to N, right? That means at D and V contains the shortest path between S to V. This statement you cannot say. You can say that D and V contains the shortest path from S to V using N edges. But that doesn't mean that that is necessarily the shortest path from S to V.
once.
Okay. Okay. Any other questions? So no other question? Okay, so if you have no other question, then you can stop here today. So this is dynamic programming. I will request you guys to go and again read up something in the book to see the dynamic programming. Dynamic programming, although it is a very simple concept, it is amazingly hard to master. Okay. So in the next class, we will be seeing some other kind of dynamic programming and a few things related to that. Okay. And we will be uploading a problem set again end of this week and an assignment sometime early next week. Okay, so if you have no other questions, I can stop today.
Thank you.
Okay, thank you.